Greetings and salutations, everybody. This is Jacob. Okay, so how the heck do we go about cracking this nut? It's a tough nut to crack, or so it seems. Worry not, my friend. I'll walk you through this problem, and pretty soon you know the ins and outs of it. You'll know the nuts and bolts. Even though this looks more complicated than the previous problem I did on pursuit curves, ironically it's a little simpler. Simpler, of course, being in the eye of the beholder. Nonetheless, you need to know some serious techniques to solve this one, my friends. So without further ado, let's get this show on the road, shall we? You're in for a real treat, my friends. Oh yes. So the problem states that 4 mice start out at the 4 corners of a square of side length 1 unit. They all have the same speed, which is constant, and each mouse pursues the mouse to its right. So since all of them have the same speeds, and they'll have the same path as well, hence we'll be focusing entirely on the mouse on the bottom left corner. So let's turn our attention to this diagram here. So our bottom left mouse is part of a Cartesian coordinate system, where its point of origin is the 0, 0 point of the Cartesian system. So since our bottom left mouse is pursuing the bottom right mouse, and its instantaneous velocity is always pointed toward the bottom right mouse, correct? In other words, the tangent to its flight path is always pointed toward mouse B. So the slope of this tangent is m equals y2 minus y1 over x2 minus x1, where y2, x2 are the coordinates of the mouse B, and y1, x1 coordinates of mouse A. Mouse A is the one doing the chasing, and the mouse B is the one that's being chased, although mouse B is also chasing the other one on the top right corner. We're only solely focusing on these 2 mice for the time being, since they all have the same path anyway. So for this problem specifically, we'll just call it the x component of mouse A's displacement x and the y component y. So when mouse A has traveled x units toward the right, then mouse B has also traveled x units towards the upper right corner. And when mouse A travels y units towards the center, then mouse B also travels y units toward the center. But as you see here, mouse B's y unit encroaches on mouse A's x component. In other words, the variables are reversed since they have the same speed and because of the symmetry of the problem. So y2 equals x and y1 equals y. So far we have dy dx equals x minus y over x2 minus x1. Okay, so what about the denominator? Notice that each side is unit length 1. So x2 minus x1 is this segment here, which is 1 minus x minus y. So now we have dy over dx equals x minus y over 1 minus x minus y. And this is the differential equation we have to solve in order to get mouse A's trajectory, correct? But notice we can't separate the variables here like we did in the previous problem. And it's a nonlinear first-order differential equation. So we can't use the standard integrating factor either. So how the heck do we go about solving this equation then? Here's where the parametric equations come in handy, my friends. Yes. We're going to introduce an independent variable, t, and express the mouse's trajectory in terms of x of t and y of t. So how do we do that? We take our Cartesian equation. On the left side, we divide the numerator and the denominator with a dt. Now we have dy over dt over dx over dt equals x minus y over 1 minus x minus y. So now we get 2 equations. Dy over dt equals x minus y, and dx over dt equals 1 minus x minus y, where x and y are in terms of t. So we turned our original Cartesian nonlinear first-order differential equation into a system of 2 linear first-order differential equations, which is solvable in this form. So is what I'm saying so far making sense? I hope it does. So moving on. How the heck do we solve a system of differential equations, you ask? So here's where the next techniques comes in handy, my friends. The next tool in our toolbox. So my friends, without further ado, I introduce to you, live and in living color, making its debut on this channel, the infamous, the immortal, the often imitated, but never duplicated, Laplace transform. Oh yes. So what is the Laplace transform, you ask? This here is the definition of the Laplace transform, f of s equals the definite integral from 0 to infinity of f of t times e to the s times t dt. So in simple terms, the Laplace transform is a definite integral that converts a function in terms of t into another function in terms of another variable, s. You could say it's a function of a function in a manner of speaking. It turns one function into another function, in other words. And we'll be using some useful properties of the Laplace transform. One such property is its linearity, namely the Laplace transform of c1 times f1 of t plus c2 times f2 of t equals c1 times big F1 of s plus c2 times big F2 of s. Another useful property is a derivative property of the Laplace transform, which is L of the derivative of f of t equals s times the Laplace transform of f of t minus f of 0. And this latter property is easy to verify using integration by parts. If you don't remember the formula for integration by parts, it's indefinite integral u times d of v equals u times v minus the integral du times v. So using integration by parts, we have definite integral of 0 to infinity of e to the negative s times t times f prime of t dt. And since f prime of t equals df over dt, and f prime of t dt equals df, and we substitute that in our previous expression, we get definite integral of 0 to infinity of e to the negative st df. Now we use integration by parts, and we get e to the negative s times t of f of t. We plug in the endpoints of that, minus the definite integral of 0 to infinity of e to the negative s times t prime times f of t dt, which is minus f of 0 plus s times the definite integral of e to the negative st times f of t dt, which is s times f of s minus f of 0. And voila, our derivative property. So the million-dollar question now is, how can we use this to solve our system of equations? By taking the Laplace transform of both sides of both equations, we can turn these differential equations into a system of algebraic equations, the two variables being big X of s and big Y of s. Big X of s is the Laplace transform of x of t, and big Y of s is the Laplace transform of y of t. And we solve these equations the same way we solve standard algebraic equations, and we transform the functions back into functions of t using the inverse Laplace transforms. Don't worry if you didn't catch all that. I'll explain it step by step, my friends. So taking the first equation, and since y of 0 equals 0 from our initial conditions, and we have the Laplace transform of the derivative of y of t equals the Laplace transform of x minus y, which is x times big Y of s equals the Laplace transform of x of t minus the Laplace transform of y of t. And we end up with s times big Y equals big X minus big Y. And this is our first equation. And we Laplace transform the second equation. And since x of 0 equals 0 from our initial conditions, then we have Laplace transform of x prime of t equals Laplace transform of 1 minus Laplace transform of x of t minus Laplace transform of y of t. So what is the Laplace transform of 1? Let's quickly work it out. So we have f of s equals definite integral of 0 to infinity of e to the negative s times t dt, which is minus 1 over s times e to the negative s times t from the endpoints of 0 to infinity. And since the exponent of e is a negative number, and if we plug in infinity to t, so e to the negative infinity is 0. So we're left with minus 1 over s times e to the 0, which is 1, which is 1 over s. So now we have s of big X equals 1 over s minus big X minus big Y. And this is our second equation. So now we just solve the system of equations algebraically. We solve for big X in the first equation, and we get big X equals s plus 1 times big Y. And we plug that in our second equation. We solve for big Y, and we get big Y equals 1 over s times s squared plus 2s plus 2. So now what do we do? Now we consult a Laplace transform table base. From the table base we have, if you have a calculus textbook, it might be in your calc textbook in the appendix somewhere, a Laplace transform table base, or in your differential equations textbook if you have one. No biggie, you can just look it up on Google. And from these table bases, we have Laplace transform of e to the alpha times t times cosine of omega t equals s minus alpha over s minus alpha squared plus omega squared. And another one is Laplace transform of e to the alpha times t times sine of omega t equals omega over s minus alpha squared plus omega squared. So here's a quick verification of the Laplace transform of e to the alpha times t times sine of omega times t using integration by parts twice, as you see here. And you do something similar with the e to the alpha times t times cosine of omega t case to verify that indeed these are the transforms of these functions, even though it's not strictly necessary because table bases don't lie. Nevertheless, I like to verify things from time to time to get our hands dirty with some techniques. In this instance, I wanted to show you the integration by parts technique since I haven't introduced it yet. So now that we got our hands dirty a little bit, what do we do now? We put the big Y of S result that we got in the form that matches the particular table bases that we just introduced. So how do we do that, you ask? Now we're going to use another time-honored method called partial fractions. Is something that you've learned from your Calc 2 class if you've taken one in college or university. If not, don't worry, I'll explain it step by step. So we want to write this expression y of s in the form a over s plus b times s plus c over s squared plus 2s plus 2, where big A, big B, and big C are constants that we have to find. So how do we find them? Remember what I said in the previous video. You combine two fractions with different denominators by multiplying the denominator of one fraction with the numerator of the other one, and you add up the terms. So we do just that here. And we have big A times s squared plus 2s plus 2 plus s times big B times s plus big C equals 1, which is big A s squared plus 2 big A times s plus 2 big A plus big B times s squared plus big C times s equals 1, which is big A plus big B times s squared plus 2 big A plus big C times s plus 2 big A equals 1. And in order for this expression to equal 1, then big A plus big B has to be 0, and 2 times big A plus big C has to equal 0, and 2 times big A has to equal 1. So big A equals 1/2, and 1/2 plus big B equals 0, and big B is negative 1/2. And we solve for C in the third equation, and we get big C equals -1. So now we found the constants, and we have 1/2 over s plus negative 1/2 times s minus 1 over s squared plus 2s plus 2, which is 1/2 over s minus 1/2 times s plus 2 over s squared plus 2s plus 2, which is 1/2 over s minus 1/2 of s plus 1 over s squared plus 2s plus 1 plus 1, which is 1/2 over s minus 1/2 times s plus 1 over s plus 1 squared plus 1 plus 1 over s plus 1 squared plus 1. So now notice these last two fractions are in the desired form that adhere to the two table bases we introduced previously, where alpha equals -1 and omega equals 1. Furthermore, the inverse Laplace transform of 1 over s is just 1. So we inverse Laplace transform the entirety of big Y of s, and we get y of t equals 1/2 minus 1/2 times e to the negative t cosine of t minus 1/2 times e to the negative t times sine of t. So that's y of t. We found y of t, my friends. One down, one to go. Luis. So we plug our y of t result into our second parametric differential equation, and we get dx over dt equals 1 minus x of t minus this expression here. So now we only have one variable, which is x of t. Now we can use the standard integrating factor that we use for first order linear differential equations. So now we have dx over dt plus x of t equals 1/2 plus 1/2 e to the negative t times cosine of t plus 1/2 times e to the negative t sine of t. We multiply both sides by e to the integral of p of x dx, which in this case is e to the t, and we get this expression here. We notice the left side is the product rule, and we integrate both sides, and we get this expression here. We divide both sides by e of t, and we end up with x of t equals 1/2 plus 1/2 times e to the negative t sine of t minus 1/2 times e to the negative t cosine of t. That's all she wrote, my friends. That's your answer. Yes. Intuitive answers or out of left field? You be the judge, my dudes, dudettes. Wow. Just wow, you guys. What a problem. Poetry in motion. Wouldn't you agree? This problem exceeded my expectations as to how beautiful it would be. Oh, yes. And no redoing calculations until the cows come home, either. Everything just fell into place. Everything just went smoothly. A lot of moving parts to this problem, of course, but I think I managed to break it down and explain it step by step, bits and pieces, so that even the average person walking the streets can understand it. Or at least if such a person has taken calculus before, you know, they have to have at least some mathematical background to understand it. But if they understand calculus, and they can understand this problem through this video. And I wanted to include another problem here, one that one of my viewers suggested. The one where one boat is chasing the other boat. The case where the chased boat is going in a parabola. I did some preliminary calculations on it, but quickly realized it's too complex to include here as a second exercise. So I'll be dedicating a whole video for that one. It's going to be my next differential equations video, my friend. I promise you. So stay tuned. I just wanted to get this one out of the way first, before sinking my teeth into the one you suggested, my friend. Ooh, yes. So I hope you liked this puzzle. Let me know in the comments what you think, if you solved it another way. If you have any questions regarding it, smash those buttons like they owe you money. You know the drill, my friends. Shoot a category and puzzle suggestion my way. And by the way, I'll be debuting new categories as we go along, like linear algebra, number theory, statistics, stuff like that. I just have to brush up on my theory of them first. That's pretty much it, my guys and gals. Take care, and I'll see you in the next video. Bye-bye.